So the first thing I want to do in this video is define what a moment is. The moment is basically an object's tendency, or a rigid body has a tendency to rotate about a given axis, or in this case a point, since we're looking at a two-dimensional case of a moment. So we have a force that's being applied to this rigid body, and what that would have, since this rigid body has some dimension with it, then there is actually a tendency for the object to rotate in this direction, since the axis of rotation occurs around this point O. So by definition, the moment is actually a vector, and the moment is equal to r cross f, where r is the distance between the axis of rotation, which is O, or point O, to the force itself. So by the principle of transmissibility, we could define F along this line, since it points in this general direction. So we could define F to be right here as well. And what we can do is define R as from this point to F, so that would be R, or this point to F, which would be R as well. So by definition, as we did before, the cross product actually gives you a vector that's perpendicular to R and F simultaneously. So in this problem, when we do the cross product, since F is pointing in this general direction, so F is going this way, and R, we'll use this one for example. So R is going this way. So when we do R cross F, we're crossing this way, and by the right-hand rule, the vector M will point outside the screen, not into the screen, but outside the screen facing towards you. And what that means is that the vector itself is perpendicular to both R and F. So what the moment vector is actually saying is that it's pointing along the axis of rotation. And since we defined R and F pointing in these directions, by the right-hand rule, the moment will cause this object to rotate in this fashion, because we're doing R cross F as we see here. So the object tends to rotate around O in this fashion. So now let's generalize this case even more, because sometimes we don't need the vector notation of the moment. Sometimes we could use the scalar quantities of the moment. So the idea of a moment is that we take some body, so let me draw another body over here. So we have some body, and let's say the axis of rotation is here. And let's say an arbitrary force, which applies over here, we'll say F, applies at some angle theta. So what we can do, we could do scalar operations to solve the actual magnitude of the vector of the moment without actually performing the cross product. So what the moment is that we take the force, and multiply it, that's probably not a good example, multiply by the perpendicular distance of that force to the axis of rotation. So let me explain that visually. So what we have here is that we have basically two components of F. So we could break F into two components, so this is going to be Fy, and this is going to be Fx. So to find the moment for Fx, what we do, we extend this line, the line of action, and then find the perpendicular distance from this line, or from this force x, and multiply it by the perpendicular distance from that line of action to the point of rotation. So we'll call this dy, and we'll do the same thing for Fy. So what we can do is multiply by this perpendicular distance, and we could define that the scalar quantity of this moment, so we could say the moment, not the vector, the moment, the magnitude, is equal to this force, Fx, dy. And then before we do this, I forgot to note that we define a right-hand coordinate system. So our object for moments, we define the axis of rotation to point this way, which is what we'll call positive, because this is a right-hand coordinate system. So you do x cross y, k will point in this direction facing towards us, So the axis of rotation will rotate in this fashion. So what we have to look at is that these forces and these perpendicular distances, we have to define what's negative and what's positive based on how they rotate. So if you could imagine this force Fx being applied along this line, and this is the perpendicular distance to O, we could assume or kind of imagine that this object will rotate in this fashion. If it's kind of hard to visualize, you'll get used to it. But if you apply a force going this way, this object will have a tendency to rotate this way, which is consistent with our definition of the right-hand coordinate system. So we could define Fx dy as positive. Now for Fy, if we imagine applying a force on this part of this distance, we could see that the object has a tendency to rotate in this fashion. Because if you just imagine like an arm sticking out of this body and you push that arm in the direction of Fy, you'll see, you can imagine that this object will rotate in a clockwise fashion. So since this is not consistent with our diagram, we have to include a negative sign. So this will be negative Fy dx. So that is how you find the scalar quantities of this moment. If you do not want to break this component or this force into components, we can actually do the same thing by using the force itself. So let me draw another example. So we have a rigid body. This is O, and we say that F is being applied in this direction again. So what we have to find the line of action, and then we have to find the perpendicular distance of F to O. See, now you can't just use any vector that points to this line of action because we're not using the cross product. So we actually have to find the only line that is perpendicular to this dashed line, which is somewhere around here. And we can only use that distance when applying the scalar quantity, when solving for the scalar quantity of the moment. So this would be some arbitrary d. So the moment for this case will be F times d. And if we assume a right-hand coordinate system as we did before, we can also imagine that if you push on this kind of lever arm, this idea of a lever arm, this object will rotate in this fashion. Just rotate around that way, which is consistent with our coordinate system, which rotates that way, and that is F times d. So there's three different ways to solve moments. The idea of an object's tendency to rotate by using the cross product. We can use the cross product, or we can break up the force into different components and multiply by the distances of each perpendicular distance of each component by the force, and we could find the magnitude of the moment by adding up the different moments based on the components. And then we also define a right-hand coordinate system, so the axis of rotation that is positive points counterclockwise. And then you could actually make it even more or simple in terms of an equation by having the line of action of the force and find one perpendicular distance to solve the scalar quantity of the moment. And again, you got to understand which way is positive and which way is negative by imagining how the force will interact with the object itself.